If you look at a suspension bridge, there is this very comforting physical logic to it.
Yeah, absolutely. You can literally just stand underneath it and understand it.
Right. You stand underneath something like the Golden Gate or the Brooklyn Bridge. You point your finger at those massive steel cables, trace the line right down to the concrete anchorages, and you can visibly see the physics of it, the tension and the compression.
It's mechanical transparency. I mean, we've spent a few thousand years building civilizations where the infrastructure is entirely tangible.
Exactly. Like if a water main breaks, you see the water flooding the street. If a road is congested, you literally see the cars backed up. You can see exactly what is holding the weight of the city.
But step into the reality of modern urban development, and that physical blueprint is, well, it's missing the most critical half of the picture.
It really is. The load-bearing pillars of a modern city are no longer just made of concrete and steel. They're made of algorithms, cryptographic hashes, and just these continuous invisible data streams.
Yeah, you are walking through an infrastructural landscape that is entirely invisible to the naked eye.
And because it's invisible, it's incredibly difficult to understand just how profoundly vulnerable and wildly advanced it actually is. So, we are taking a deep dive today into that exact invisible infrastructure. Our mission for you today is to unpack the fascinating, super complex synergy between deep learning and blockchain technology.
Right, we're looking at how these two massive, seemingly contradictory technological forces are fusing together to build the smart and sustainable cities of the future.
But we have a really comprehensive stack of source material to do this. We're pulling directly from a textbook titled Deep Learning and Blockchain Technology for Smart and Sustainable Cities,
Which is edited by V. Subramaniaswamy alongside several other leading researchers. And what makes this text so vital is that it bridges a massive gap.
Right out of the gate, that's the hook for you today. Because, we hear about artificial intelligence constantly.
Yeah, nonstop.
And we hear about crypto and blockchain constantly, too. But we almost always hear about them in complete isolation from one another. Like, AI is the mysterious black box taking over cognitive tasks, and blockchain is just the volatile engine behind digital currencies.
Yeah, but their fusion is quietly revolutionizing the physical world around you.
Exactly. We're talking about the exact physics of how you sit at a traffic light, or how we deploy emergency care for the elderly, or even the literal soil chemistry used to grow the food on your table.
When you combine them, they actually solve each other's most glaring structural weaknesses. It's an elegant, almost biological symbiosis.
Okay, let's unpack this. Because to understand the applications, we really need to understand the mechanism first.
Right, the how.
Yeah, if deep learning is the brilliant obsessive detective, right, analyzing millions of seemingly disconnected clues and finding hidden patterns in the absolute chaos of a city.
Then blockchain is the incorruptible, mathematically sealed evidence room, keeping all of that raw data perfectly safe, time-stamped, and verifiable.
I love that analogy. But before we get to the roads and the hospitals, let's establish the exact nature of this data. Because a smart city isn't just generating a few spreadsheets, is it?
Not even close. To understand the scale, you really have to look at the deployment of the Internet of Things, or IoT.
Right.
A smart city is essentially a living organism covered in billions of sensory nerve endings. We are talking about optical sensors on streetlights, thermal cameras at intersections, HVAC thermostats in commercial high-rises,
Moisture and chemical detectors embedded in the soil of public parks. Gyroscopes in wearable medical devices.
Exactly. It's a continuous, unrelenting fire hose of raw telemetry. You have a single intersection generating gigabytes of data an hour. Vehicle velocity, pedestrian density, ambient temperature, air quality metrics, it just never stops.
And raw data in that volume is fundamentally useless to a person.
Completely useless. Human operators cannot monitor a billion sensors. That is where deep learning, the brains of the operation, becomes mandatory.
So these deep learning algorithms, specifically complex neural networks, they're deployed to ingest that fire hose.
Yeah, and they don't just record the data. They actually learn the underlying architecture of the city's behavior. They analyze the streams to identify multivariable patterns.
Give me an example of that. What does that actually look like?
Well, a human might notice that traffic backs up on 4th Street when it rains. That's a simple observation.
Right.
But a deep learning model realizes that traffic backs up on 4th Street when the barometric pressure drops, combined with a 5% increase in rideshare activity in the financial district and a localized spike in power grid usage.
Wow. So it identifies correlations that are completely invisible to human cognition.
Exactly. It provides the intelligence to preemptively reroute traffic or adjust the power grid before a brownout even occurs.
But having read through the text, I see a glaring, almost catastrophic vulnerability in this setup.
The centralization of the data.
Exactly. Deep learning models are entirely dependent on the integrity of their training and operational data. I mean, garbage in, garbage out, right? If they ingest bad data, they output bad decisions.
And in a smart city, this data isn't just weather patterns. It's your exact real-time location. It's the layout of the city's power grid. It's live telemetry from medical devices.
So if a centralized municipal server is holding all of that, it becomes the ultimate honeypot for a cyber attack.
It's the single point of failure. If a malicious actor infiltrates that central database and subtly alters the incoming data,
Say, feeding the traffic algorithm false sensor readings that make a clear intersection appear heavily congested.
right, the deep learning model will react dynamically. It will reroute thousands of cars into an artificial bottleneck, effectively paralyzing the city's infrastructure without the hacker ever needing to touch a physical traffic light.
The detective is brilliant, but if the evidence has been tampered with before the detective even sees it, the resulting conclusion is disastrous.
Which means we need a way to mathematically guarantee the integrity of the data stream. Enter the trust layer.
The evidence room.
Exactly, blockchain. The text outlines how blockchain architecture solves the vulnerability of centralized IoT data through immutability and decentralization.
But I need you to break down how that actually functions on a mechanical level. Because people hear blockchain and they think of a database. And a database is just a digital filing cabinet. You can open a file, change the numbers, and save it.
Yeah, but blockchain is structurally different from a database because of cryptographic hashing.
Okay, walk me through that.
When a sensor in the smart city generates a piece of data, say an air quality reading, that data is run through a mathematical algorithm, typically something like SHA-256.
Right.
This algorithm takes the data and produces a fixed-length string of letters and numbers called a hash. This hash acts as a unique digital fingerprint for that specific data.
And the crucial part of hashing is the avalanche effect.
Yeah, precisely. The avalanche effect means that if someone tries to alter even a single decimal point in that air quality reading, the resulting hash changes completely. The new fingerprint won't match the old one at all.
So that provides the immutability. You can't secretly change the data. But what about the decentralization part?
Well, instead of storing this data on one central municipal server, the blockchain distributes an exact copy of the ledger across thousands of independent computers or nodes across the network.
Okay.
Before a new block of data is added to the chain, these nodes must reach a consensus. They mathematically verify that the hashes match. If a hacker tries to alter the data on one node, the other 9,999 nodes look at their copies, see that the hashes don't match the corrupted node, and instantly reject the altered data.
So the evidence room isn't just a single vault with one guard. It's 10,000 identical vaults scattered across the globe with 10,000 guards who constantly audit each other's ledgers simultaneously.
That's exactly it. You can't bribe one guard. You'd have to simultaneously bribe 5,001 of them in the exact same millisecond to falsify a record.
Which is mathematically impossible, or practically impossible.
Right. That cryptographic consensus allows this incredibly sensitive, massive volume of city data to be shared and utilized securely without relying on a vulnerable central authority.
So the deep learning algorithms can pull verified, untampered data to make their predictive models, and the citizens can trust that their behavioral data isn't being manipulated.
Exactly.
I understand the security aspect, but I'm going to push back on the logistics here.
Yeah.
Because anyone who has interacted with early blockchain networks knows they are notoriously slow.
Oh, for sure.
I mean, Bitcoin transactions can take 10 minutes to clear. Ethereum can get congested and cost exorbitant gas fees. A traffic light cannot wait 10 minutes for thousands of global nodes to achieve consensus on whether a car is approaching. It needs to react in milliseconds.
It absolutely does.
So how on earth can a decentralized ledger operate fast enough to run a physical city?
That is the defining hurdle. And what's fascinating here is how the architecture of smart city blockchains bypasses the latency of those early cryptocurrencies. They do this through a combination of edge computing and localized smart contracts.
I really want to focus on smart contracts because it's a term thrown around constantly, usually with that tired analogy of a digital vending machine.
Right, you put $1 in, the machine verifies it and gives you a soda.
Yeah, but that doesn't really explain how a decentralized network replaces human decision-making at the speed of a city intersection.
Let's use a more accurate mechanical analogy then. Think of a smart contract not as a vending machine, but as an incredibly complex, self-assembling piece of digital clockwork that only locks into place when exact mathematical conditions are met by the network.
Okay, so it's essentially self-executing code deployed directly onto the blockchain.
Exactly. So instead of a central computer actively deciding to turn a light green, the logic is embedded in the network itself.
So the smart contract contains the logical parameters. Like, if sensor A detects an ambulance, ND sensor B detects cross-traffic is clear, then change the light to green.
Right. But here's how it achieves the speed. Smart city blockchains often utilize layer 2 protocols or state channels.
Break that down for me. What is a state channel?
Well, instead of broadcasting every single micro interaction, like every millisecond of a traffic light changing to the entire global blockchain to be heavily validated and permanently stored.
Which would take forever.
Exactly. Instead of doing that, a state channel opens a localized temporary cryptographic tunnel between the specific devices at that intersection.
Ah, so the local sensors and the traffic light are communicating directly and securely with each other. They're executing the smart contract logic instantly off the main chain.
Yes. They run the transactions locally at lightning speed. Then, periodically, say once an hour, the net result of all those local transactions is bundled up, hashed, and settled onto the main blockchain for permanent, immutable storage.
Okay, that makes vastly more sense. You get the millisecond execution speed required for a physical city, backed by the impenetrable security of the decentralized ledger.
Exactly. It's local execution with global verification.
So we have the brain's deep learning analyzing the complex patterns, and we have the trust layer blockchain securing the data and automating actions instantly via smart contracts. We've established the digital physics of the city.
Right, the foundation.
Let's look at how this manifests in the physical world, specifically how we navigate it, the transportation grid.
The textbook dedicates a substantial amount of research to intelligent transportation systems, or ITES, and this is where the fusion of these technologies becomes immediately visible to the daily commuter.
The sources outline some wild capabilities for deep learning on the roads, because we aren't just talking about a GPS app noticing that cars are moving slowly and coloring the map red. We're talking about predictive fluid dynamics applied to urban traffic.
That's a highly accurate way to frame it. Traditional traffic management is reactive. Even the better systems just use induction loops in the pavement to sense a car is waiting and trigger a green light.
But they have no spatial awareness.
Entirely blind. But in a smart city, deep learning models ingest real-time video feeds from edge-processed street cameras, combine that with GPS telemetry from thousands of connected vehicles, and factor in historical congestion patterns.
And the goal isn't just to react to a traffic jam, but to predict the formation of a phantom traffic jam before it even solidifies.
Exactly, phantom jams. They occur when a single driver brakes slightly on a highway, causing the driver behind them to brake slightly harder. It creates this backward propagating wave of congestion that can bring a highway to a standstill for literally no physical reason.
Right, there's no accident, just a wave of braking.
Deep learning algorithms detect the initial preconditions for these waves. They can dynamically optimize signal timings across a 10-square-mile grid, subtly altering the flow of vehicles to diffuse the wave before it even forms.
And the text mentions actual implementations of this. Shanghai, for instance, uses deep learning to optimize its entire public transit routing system dynamically. It adjusts schedules based on real-time passenger density and traffic conditions.
Yeah, and Dubai has gone a step further, launching an initiative they literally refer to as the road blockchain.
Which highlights the other half of the synergy. If deep learning is predicting the flow and routing the vehicles, the blockchain is securing the communication network between those vehicles. Vehicle-to-everything, or V2X communication.
And enabling seamless economic interactions.
Micropayments. This is a concept that fundamentally alters the friction of living in a city.
Oh, absolutely. Think about the immense friction involved in simply moving through an urban environment today. You have a reloadable card for the subway system, an app for a ride share, a physical transponder stuck to your windshield for toll roads, and an account tied to a credit card for parking meters.
It's a fragmented nightmare, just different databases, payment processors, and physical tokens.
Blockchain unifies the economic layer of the city. It acts as a universal, decentralized ledger for mobility. Because smart contracts can execute transactions in milliseconds without a centralized bank clearinghouse taking a percentage or causing a delay, it allows for true microtransactions.
So imagine you're driving your electric vehicle down a smart highway. Your car's deep learning navigation is constantly communicating with the grid to find the optimal path. You cross into a congestion pricing zone.
Right.
Instead of a camera flashing and mailing you a bill weeks later, a smart contract on the blockchain instantly deducts 3 cents from your vehicle's digital wallet. You merge into an express lane for exactly 4 miles, and the smart contract streams a fraction of a cent per mile directly to the municipality's wallet.
And this extends to public transit too. You could walk onto a bus, step off, hop onto a shared bicycle and park it near your office. The blockchain seamlessly logs your cryptographic identity and automatically settles the complex microfares across different transit providers instantly.
The textbook also highlights peer-to-peer ride-sharing. This completely undercuts the current corporate model of ride-hailing apps, because instead of a massive tech company acting as the middleman, taking a 30% cut and storing all your location data on their centralized servers.
The blockchain connects the rider and the driver directly. The smart contract holds the fare in escrow. Once the vehicle's GPS verifies the destination has been reached, the contract releases the funds to the driver instantly,
It maximizes efficiency for the driver and lowers the cost to the rider.
while keeping the location data completely secure on the decentralized ledger.
But the metric that truly caught my attention in the source material wasn't financial, it was environmental. By implementing these specific systems, the predictive deep learning routing combined with frictionless blockchain interaction cities are documenting a 10% to 15% reduction in overall fuel usage and vehicular emissions.
That is a staggering reduction, and it really comes down to the physics of idling. Internal combustion engines are horrifically inefficient when a vehicle is stationary or constantly accelerating and decelerating.
Right.
By maintaining a continuous, optimized flow preventing vehicles from idling at inefficient red lights when there is no cross traffic, and eliminating the need for cars to circle city blocks for 20 minutes looking for a parking spot because the network already reserved an open spot via a smart contract, you drastically reduce the carbon output of the grid.
But, there is an inherent ceiling on how much efficiency matters if the people inside those seamlessly flowing cars are heading toward an overburdened hospital.
That's a great point.
Because the physical flow of a city is irrelevant if the biological health of its citizens collapses.
That is the core tenet of sustainability in the textbook. A smart city must prioritize the physiological well-being of its population. This integration is referred to as medical cyber-physical systems, or MCPS, fused with the Internet of Things.
Healthcare in a modern city is currently plagued by the exact same centralization issues we discussed earlier, just with significantly higher stakes.
Much higher.
The current model relies on siloed databases. Your primary care physician has one set of records, the local hospital has another, and a specialist across town has a third. And they are all sitting on vulnerable, centralized servers.
The shift detailed in the text moves toward a patient-centered, decentralized model utilizing electronic health records, or EHRs, anchored on the blockchain.
Let's explore how that actually functions, because medical data is governed by strict privacy laws, like IPA in the U.S. You can't just post someone's medical history to a public ledger.
No, absolutely not. This requires a specific type of blockchain implementation, often a permissioned or consortium blockchain combined with advanced encryption. The blockchain itself doesn't store the massive files of your MRI scans or your entire medical history in plain text.
Oh?
It stores the cryptographic hash, the digital fingerprint of your records, along with a pointer to where the encrypted data is actually stored on a secure, distributed file system.
So the blockchain acts as an immutable index, like a highly secure card catalog.
Yes. And you, the patient, hold the private cryptographic key. If you visit a new emergency room in the smart city, you use a smart contract to temporarily grant the attending physician access to your complete, untempered medical history.
And then?
The moment you leave, the smart contract can automatically revoke that access.
It fundamentally flips the ownership of medical data back to the individual. But where does the deep learning component enter the healthcare equation?
Well, deep learning thrives on large data sets. While individual patient data is locked behind private keys, smart contracts can allow for the secure, anonymized pooling of health telemetry.
Right.
Deep learning models can analyze this aggregate data to predict urban health trends. They can monitor anonymized thermal camera data from transit hubs, combined with localized pharmaceutical purchase data to predict a viral outbreak days before hospitals see a surge in admissions.
The text specifically highlights the use of convolutional neural networks, or CNNs.
Yes. CNNs are a class of deep neural networks specifically designed for processing structured arrays of data, Primarily images, they are incredibly adept at recognizing visual patterns.
And the book discusses deploying CNNs directly onto the blockchain to analyze medical imaging, like X-rays or MRIs.
The integration works like this. An MRI machine generates a scan. That scan is instantly hashed and secured via the blockchain to guarantee it hasn't been altered. The CNN algorithm then processes the verified image, looking for minute anomalies, early-stage tumors, or microfractures that a human radiologist might miss in a state of fatigue.
Wow.
The CNN provides an instant, highly accurate diagnostic probability, accelerating the whole triage process.
It's an incredible application of computational power, but the specific use case in the source material that truly illustrates the life-saving potential of pushing this technology to the absolute edge of the network is elderly care, specifically fall detection.
It seems like a hyper-specific issue compared to, urban traffic grids. But the epidemiological statistics in the text frame it as a quiet, pervasive crisis. Falls are the leading cause of fatal and non-fatal injuries for older adults.
We're talking about 160 million senior citizens currently residing in the U.S. and Europe who are at high risk.
And traditional mitigation relies on those medical alert pendants. The classic, I've fallen and I can't get up buttons.
Which are fundamentally flawed pieces of technology. They require the user to be conscious, lucid, and physically capable of pressing a button after a traumatic event has already occurred.
Right. They are purely reactive and often fail when they are needed most.
So the smart city approach to this problem is a masterclass in edge computing and sensor integration. The textbook details an array of non-intrusive IoT hardware deployed in the homes of elderly citizens. We aren't just talking about a camera in the corner. We are talking about wearable sensors equipped with high-fidelity accelerometers and gyroscopes.
The text also mentions myoware sensors, which are fascinating.
What are those exactly?
They are electromyography sensors that measure the electrical activity produced by skeletal muscles. They literally monitor muscle activation patterns in real time.
They even deploy GPS-enabled smart soles placed inside shoes and arrays of sensors mounted directly onto the chassis of wheelchairs, constantly gathering real-time telemetry on movement, gait stability, and velocity.
But this brings us back to the primary challenge of the IoT fire hose. If a wearable accelerometer registers a sudden, rapid downward velocity followed by an impact, how does the system know the person actually collapsed?
Right, because if I forcefully throw myself onto the living room couch after a long day, the raw accelerometer data looks remarkably similar to a dangerous fall.
Exactly.
If the system sends an ambulance every time someone sits down quickly, the city's emergency services would be paralyzed by false alarms within a week.
This is exactly where the deep learning analysis becomes a matter of life and death, and why it must happen at the edge.
The text heavily emphasizes algorithms called boosted decision trees for this specific task. Explain why they used this specific mathematical model instead of a massive neural network.
It comes down to computational efficiency versus accuracy. A massive neural network requires significant processing power and memory. But you can't strap a supercomputer to an elderly person's wrist.
No, obviously not.
You need an algorithm that is lightweight enough to run locally on a tiny microchip, an edge device, but accurate enough to distinguish between a couch flop and a cardiac collapse.
So how does a boosted decision tree achieve that?
Well, a standard decision tree is simple. It asks binary questions. Was the downward acceleration greater than X? Did the gyroscope register a tilt greater than Y? But a single tree is prone to errors. Boosting is an ensemble technique. The algorithm creates a sequence of simple decision trees.
Okay, a sequence.
The first tree analyzes the data and inevitably makes some mistakes. The second tree is specifically trained to focus on the data points that the first tree got wrong. The third tree focuses on the errors of the second, and so on.
So it's a cascading series of algorithms, each one mathematically correcting the blind spots of the one before it, until they collectively form a highly accurate prediction model.
Exactly. And because the individual trees are simple, the compiled model is incredibly fast and requires very little computational overhead. The boosted decision tree runs directly on the wearable sensor. It analyzes the complex telemetry of the accelerometer, the gyroscope, and the muscle activation locally in milliseconds.
Wow.
It recognizes the specific multivariable physical signature of a genuine fall with extreme accuracy.
Okay, so the physics of the fall occur. The IoT hardware registers the telemetry. The boosted decision tree algorithm running on the edge device instantly verifies, yes, this is a catastrophic fall, not a false alarm. What is the exact sequence of events that follows?
This is where the blockchain executes the critical response. The moment the deep learning model verifies the fall, it signs a cryptographic transaction that triggers a smart contract deployed on the healthcare blockchain.
So there is no waiting for a human dispatcher.
None. The smart contract executes instantly. It utilizes the patient's decentralized identity to automatically securely alert designated caregivers, family members, and the nearest emergency medical services.
And because it's integrated with the blockchain EHR system, it doesn't just send a panic signal. It sends a secure, temporary cryptographic token, granting the responding paramedics access to the patient's critical medical history.
Right, their blood type, allergies, current medications.
Furthermore, the GPS smart soles, or the wheelchair sensors, provide the exact encrypted spatial coordinates. The paramedics know precisely who fell, their medical vulnerabilities, and exactly which room in the building they are located in before they even start the ambulance.
It creates an unbreakable, autonomous chain of survival. It removes human latency from the emergency response protocol. It allows elderly citizens to maintain their dignity and independence, knowing the invisible infrastructure is actively guarding them.
It's a profound application. But that localized device-level processing, the edge computing we just discussed on a wheelchair sensor, is actually the exact same computational principle that solves a completely different urban crisis.
You're referring to the logistics of the food supply.
Exactly. We've moved the citizens seamlessly, and we've secured their health. But a massive, densely packed urban population requires an astronomical amount of caloric intake to survive. A smart city must secure its food supply, which brings us to the integration of these technologies into agriculture, smart farming.
It represents a fascinating geographic shift in the application of the technology. We tend to view agriculture as inherently low-tech and entirely separate from urban infrastructure.
Right.
But food security is the foundational pillar of any city. The textbook explores how IoT and deep learning are literally being embedded into the soil, both in vertical urban farms and in remote rural agricultural zones that feed the city.
The deployment of sensors in a smart farm mirrors the traffic grid, but the metrics are entirely biological. The text outlines IoT sensors continuously monitoring soil moisture gradients, ambient humidity, temperature fluctuations, and even utilizing spectral imaging.
Spectral imaging to monitor the chlorophyll levels in crop leaves to detect early signs of blight or nutrient deficiency.
And just like the traffic data, this biological telemetry is fed into advanced machine learning models. The text specifically highlights the use of an algorithm called XGBoost for crop yield prediction.
XGBoost.
Extreme gradient boosting. You see this algorithm dominating machine learning competitions constantly. Why is it so effective for something as chaotic as farming?
Well, farming is an incredibly complex predictive challenge because the variables are highly nonlinear. You are dealing with soil chemistry interacting with unpredictable weather patterns and biological growth cycles. Traditional statistical models simply cannot map those relationships accurately.
So XGBoost steps in.
Yes, XGBoost, similar to the boosted trees we discussed for fall detection, builds sequential decision trees.
But the extreme part implies a different mathematical mechanism.
It does. XGBoost utilizes a highly optimized mathematical process involving second-order derivatives to minimize a specific loss function. Essentially, it is incredibly efficient at calculating exactly how wrong its previous predictions were and adjusting its parameters with hyper-precision to correct the residuals.
So what does that actually mean in the context of a farm?
It means the algorithm can take the real-time sensor data from the soil, the exact moisture and nitrogen levels, and correlate it against a century of historical meteorological data, rainfall patterns, and localized temperature fluctuations.
Wow.
It processes this massive historical data set against the current live telemetry to predict exact crop yields for specific microclimates.
And the textbook details how this hyper-complex, century-spanning mathematical analysis is distilled into an incredibly intuitive interface for the end user. Because the farmer isn't required to understand second-order derivatives.
No, not at all.
The book describes an application where the farmer simply opens a dashboard on a tablet. The interface displays a straightforward probability matrix, perhaps a pie chart or a simple percentage breakdown.
It translates algorithmic complexity into actionable intelligence.
Right. The interface might show a 13.9% probability of optimal yield for cotton, a 13.5% probability for maize, and an 8% probability for soybeans, based on the exact soil chemistry recorded 3 seconds ago, combined with the 60-day weather forecast.
So the farmer looks at the data and plants exactly what the algorithm dictates will maximize caloric output and financial survival for that specific season.
It completely removes the guesswork and the reliance on intuition. replacing it with hard, predictive mathematics. But I see a massive infrastructural bottleneck here.
Ooh.
Yeah. We just discussed how resource-intensive these models can be. It's one thing to run a lightweight model on a wheelchair to detect a sudden movement. It's entirely different to run an XGBoost model analyzing a century of climate data. A vertical farm in the center of a smart city has access to fiber optic internet and massive server racks. But the rural farms producing the bulk of the food supply absolutely do not. So how do you deploy this technology in areas with terrible bandwidth?
That is a critical logistical hurdle, and the textbook introduces a fascinating architectural solution called osmotic computing.
I am familiar with osmosis in a biological context. It's the movement of solvent molecules through a semi-permeable membrane to equalize the concentration of a solute on both sides.
Yeah.
But how does biological fluid dynamics map to computer networking?
It maps beautifully, actually. In a smart city network, osmotic computing is the dynamic fluid allocation of computing resources based on the immediate needs and limitations of the network.
Okay, let's explore the mechanics of that.
If a rural farm is generating gigabytes of spectral imaging data from its crops every hour, it simply cannot push that raw data stream over a weak rural internet connection to a centralized cloud server for processing. The bandwidth isn't there. The latency would be unacceptable.
So the network adjusts the concentration of processing power.
Exactly. The osmotic computing framework detects the bandwidth limitation and dynamically pushes the deep learning analysis down to the edge. It migrates the machine learning models from the central cloud server directly to local gateways or micro data centers situated right there on the farm.
Oh, I see. So the heavy computational lifting, the XGBoost processing the centuries of weather data against the live soil metrics is executed locally on the farm's hardware.
Yes. And once the algorithm has processed the raw data and generated the final, highly condensed insight, the simple probability matrix for the crop yield, only that tiny packet of insight is transmitted back over the weak internet connection to the broader smart city network.
It prevents the network from suffocating under the weight of raw telemetry.
Right.
It democratizes the intelligence, allowing even the most remote agricultural zones to fully integrate into the smart city ecosystem without requiring a multi-million-dollar fiber optic infrastructure project.
It's an incredibly elegant solution. But growing the food efficiently is only the first phase. In a smart city context, the logistics of distributing that food securely to millions of citizens is where the blockchain becomes paramount. We are talking about supply chain traceability.
The physical journey of the calories.
From the precise moment a seed is planted in the monitored soil, its journey is cryptographically anchored. When the crop is harvested, the IoT sensors on the combine harvester automatically log the exact GPS coordinates, the time, and the ambient temperature onto the blockchain.
And a hash is generated.
Correct. When the crop is transferred to a refrigerated transport truck, the IoT thermal sensors in the trailer continuously record the temperature throughout the journey, automatically logging that data to the blockchain via smart contracts.
So if the temperature in the truck rises above a safe threshold for even 10 minutes, the smart contract flags that specific batch as compromised.
It creates an unbroken, mathematically verifiable chain of custody. And the textbook illustrates how this impacts the consumer at the end of the line. Imagine you are standing in a grocery store in the smart city. You pick up a package of organic strawberries. Printed on the label is a simple QR code.
You scan it with your smartphone, and because the entire supply chain is anchored to the decentralized ledger, you instantly receive the complete immutable history of those strawberries.
You can see the exact plot of land they were grown on. You can view the soil quality metrics from the day they were planted. You can verify that the farm adheres to ethical labor practices. You can see the exact temperature they were kept at during transport.
It entirely eliminates the possibility of food fraud, where conventional crops are mislabeled as premium organic because you simply cannot retroactively fake a cryptographic hash.
But beyond ethical consumption, it serves as a critical defense mechanism for public health. Rapid recall. If there's an outbreak of E. coli or Salmonella, the current centralized system is chaotic. Authorities have to guess where the contamination originated, often resulting in the precautionary destruction of thousands of tons of perfectly safe food across multiple states.
In the blockchain-enabled smart city, the response is surgical. The authorities query the ledger, trace the contaminated batch back through the hashes, and identify the exact processing facility or farm responsible within seconds.
They can instantly issue targeted recalls for only the specific packages that pass through that facility at that specific time, isolating the threat while preventing massive food waste.
So we have the soil monitored, the crop yields mathematically optimized, and the food tracked with cryptographic precision. But crops and people both share one unavoidable continuous intake that dictates their health: the air.
Which leads us directly to environmental monitoring and the Air Quality Index, or AQI. This is an incredibly difficult metric for urban planners to manage because the variables are highly dynamic.
The textbook points out a glaring flaw in how we currently monitor air quality. A city might place a few dozen physical air quality sensors on the roofs of municipal buildings and assume that data accurately represents the entire metropolitan area.
It's a vast oversimplification. Urban air quality is hyper-localized and constantly shifting based on incredibly complex chemical and meteorological interactions. You have nitrogen dioxide emitted from the traffic grid we discussed earlier.
We have sulfur dioxide from industrial zones on the outskirts.
You have ground-level ozone formation. And you have particulate matter, specifically PM2.5, which is deeply damaging to respiratory health.
And all of those pollutants are constantly interacting with shifting wind vectors, temperature inversions, and the physical topography of the urban architecture itself, the way skyscrapers channel or block airflow.
A standard statistical model cannot account for those chaotic variables. Deep learning is deployed to analyze the multivariate interactions. But here's the specific detail from the textbook that truly showcases the power of algorithmic inference.
What's that?
Deep learning models can accurately predict the exact air quality in zones of the city that have absolutely zero physical monitoring stations.
Okay, I need to understand the mechanics of that. If there is no sensor gathering data in a specific neighborhood, how is the system not just blindly guessing?
It's not guessing. It is performing highly advanced, multivariate spatiotemporal interpolation. The neural networks analyze the regional geographical links. They ingest the data from the sensors that do exist, and then they correlate that with real-time meteorological data, wind speed, humidity, temperature.
They're essentially modeling the fluid dynamics of the atmosphere.
Exactly. They also factor in the chemical dispersion models, how specific pollutants react to sunlight and drift over time, combined with the real-time traffic density data from the transportation grid.
Oh, wow. So if the system knows there is heavy congestion on a highway to the west, and it knows the wind is blowing at 12 miles per hour to the east, and it understands the atmospheric chemistry of nitrogen dioxide,
The deep learning model can mathematically deduce the exact concentration of pollutants that will arrive in the unmonitored residential neighborhood to the east with astonishing precision. It fills in the physical blind spots of the city's sensory network using pure computational logic.
it effectively creates virtual sensors out of math. That is brilliant. But where does the digital ledger fit into this? How does a blockchain improve the physical environment?
It introduces rigid, unavoidable accountability to environmental regulations. The text provides a concrete scenario regarding industrial emissions and carbon credits. Imagine a manufacturing facility operating on the edge of the smart city. Under current paradigms, environmental compliance is often an honor system backed by occasional audits.
Right. A factory might pollute heavily during the night shift and simply alter the internal spreadsheets before submitting the emissions report to the Environmental Protection Agency.
Precisely. But in this architecture, IoT emission sensors are installed directly into the smokestacks of the facility, and those sensors are cryptographically linked to the blockchain.
Every cubic meter of sulfur dioxide emitted is instantly hashed and permanently logged on the decentralized ledger.
It creates an immutable, entirely transparent record of the facility's environmental impact. The factory management simply cannot alter the data retroactively to hide a spike in toxic emissions because they cannot rewrite the blockchain. The ledger guarantees the integrity of the environmental data.
And because that data is universally trusted, it enables the automation of regulatory enforcement via smart contracts.
Yes. The smart contracts can be programmed to automatically monitor the immutable emissions data against the legal thresholds. If the factory exceeds its permitted carbon output, the smart contract autonomously levies a financial penalty directly from the company's digital wallet.
Conversely, if they operate under the limit, the smart contract can automatically issue renewable energy certificates or carbon credits, which the company can instantly trade on a decentralized exchange. It removes the bureaucracy of environmental compliance and replaces it with inescapable, automated mathematical enforcement.
The textbook also highlights how this predictive optimization extends to physical waste management. They discuss the deployment of IoT smart bins distributed across the city.
Trash cans equipped with ultrasonic sensors to detect exactly how full they are.
Yes. Think about the massive inefficiency of traditional waste management. A fleet of diesel garbage trucks drives a fixed, predetermined route every single Tuesday. They waste immense amounts of fuel stopping to check bins that are completely empty, while ignoring bins 3 streets over that have been overflowing for
It's
days.
the traveling salesman problem, but applied to thousands of dynamic nodes.
And deep learning excels at solving dynamic routing problems. The algorithm ingests the fill-level telemetry from every smart bin in the city. It then calculates the most mathematically efficient route for the waste collection fleet on that specific day, directing the trucks only to the bins that actually require emptying.
The textbook notes that this seemingly simple optimization, when scaled across a major metropolitan area, cuts waste collection vehicular emissions and fuel consumption by 15% to 20%.
That's huge.
It's a massive environmental gain achieved purely through algorithmic efficiency.
It is. But as we continually stack these layers of complexity, the real-time processing of traffic fluid dynamics, the instant cryptographic verification of medical telemetry, the continuous atmospheric modeling, the dynamic routing of physical waste, we arrive at a fundamental physical limitation.
The bandwidth. We are talking about billions of IoT devices chattering constantly, generating petabytes of data, demanding millisecond latency. The communication infrastructure required to handle this is staggering.
Which brings us to the nervous system of the smart city, the telecommunications architecture. We are currently rolling out 5G networks globally, but the textbook is explicitly focused on the necessity of 5G beyond and the emerging 6G networks.
The sheer volume of data makes my head spin. If every autonomous vehicle, every streetlight, every elderly citizen's biometric sensor, every crop monitor, and every trash can is continuously transmitting and receiving complex cryptographic hashes, how does the physics of 6G actually differ from what we have now to accommodate that load?
If we connect this to the broader evolution of telecommunications, 6G isn't just a linear increase in download speeds so you can stream a movie faster. It represents a fundamental paradigm shift in network architecture. 6G operates on the terahertz frequency bands, which allows for astronomical data transfer rates. But more importantly, it facilitates a completely decentralized network topology pushed to the extreme edge.
It minimizes latency to a degree that makes real-time automation viable.
Exactly. Latency is the physical delay between a sensor sending a data packet and receiving the algorithmic response. If you are a fully autonomous vehicle approaching a pedestrian crossing and the deep learning model running in the cloud detects an anomaly, you cannot afford a 50-millisecond delay for the braking command to travel back to the car.
Right.
6G infrastructure aims for sub-millisecond latency.
But the textbook highlights a fascinating bottleneck that arises even with 6G and how the blockchain is used to solve it. It's an issue of radio spectrum.
Yes, the actual invisible electromagnetic frequencies that all of this data travels on. Radio spectrum is a finite physical resource.
Currently, spectrum allocation is incredibly rigid. Government entities like the FCC in the United States auction off specific frequency bands to major telecom corporations. It's a highly bureaucratic, heavily centralized process.
And it leads to massive inefficiencies. A telecom company might own a large block of spectrum, but at 3.0 a.m. in a specific neighborhood, they might only be using 5% of its capacity. Meanwhile, another network in the same area might be overloaded, dropping packets because it can't dynamically access the unused frequencies.
So how does the integration of 6G and blockchain fix the centralized spectrum bottleneck?
Through a mechanism called dynamic spectrum sharing and auctioning, 6G networks will utilize cognitive radios devices that can automatically detect which frequencies are currently available in their immediate vicinity. But to prevent chaos and collisions, you need a way to manage who has the right to use those frequencies millisecond by millisecond.
And a central clearinghouse is too slow.
Exactly. So the blockchain acts as an automated high-speed spectrum broker. The textbook outlines a system where smart contracts facilitate microtransactions between primary users, the entities that legally own the spectrum license, and cognitive users, the billions of IoT devices that need to borrow a fraction of bandwidth for a millisecond.
So the devices themselves are autonomously negotiating for airspace.
Yes. Imagine a surge in data traffic, perhaps a localized emergency requiring massive biometric data transmission. The primary user smart contract instantly detects the demand and automatically auctions off its unused spectrum capacity on the blockchain.
Wow.
The cognitive devices bid microfractions of a cent for access. The smart contract verifies the cryptographic funds and grants access to the frequency block.
All of this complex economic and physical negotiation is happening autonomously, millions of times a second, governed entirely by decentralized math. It ensures the network never crashes due to artificial scarcity, optimizing the invisible traffic in the air just as the deep learning algorithms optimize the physical traffic on the roads.
It's a beautifully self-regulating system. But constructing a hyper-connected, hyper-fast, fully automated city built on billions of interacting nodes raises the most terrifying question of this entire deep dive.
Right. We have built an incredibly efficient, unfathomably complex machine. What happens when a sophisticated actor attempts to destroy it?
The threat landscape. This is the final and most critical segment of the textbook's analysis, the immune system of the city.
The vulnerabilities outlined in these sources are chilling because the stakes are no longer just digital. A cyber attack 50 years ago meant someone defaced a website. 20 years ago, it meant someone stole credit card numbers.
But in the architecture we discussed today, a cyber attack is a kinetic threat. A coordinated breach of the smart city's energy grid algorithms could induce rolling blackouts that shut down life support systems in hospitals.
Right.
Unauthorized access to the V2X communication grid could manipulate the deep learning traffic models to deliberately crash autonomous vehicles at highway speeds.
The theft of decrypted health data, the manipulation of the water purification sensors. It is the ultimate high-stakes environment. A digital breach translates instantly to physical devastation.
Which is why the textbook details a comprehensive defensive posture called the SMART VS framework.
Break down that acronym.
It stands for Vulnerability, Attacks, Security, and Threats. It is a systematic methodology for anticipating and mitigating every conceivable vector of attack in a hyper-connected urban environment. And within this framework, the blockchain is unequivocally positioned as the core immune response.
I want to dig deep into the exact cryptography here. We discussed hashing earlier. But how does the network mathematically, physically, or rather digitally repel an organized assault on the infrastructure?
The textbook focuses heavily on the deployment of asymmetric cryptography, also known as public key cryptography. This is the mathematical foundation of the blockchain's security.
How does the math actually work to prevent a hacker from injecting a malicious command to, say, open the floodgates of a municipal reservoir?
Asymmetric cryptography relies on mathematically linked pairs of keys. Every node, every device, and every human user on the network is issued a public key and a private key. The public key is visible to everyone. It acts like an address. But the private key is held exclusively by the owner.
And the mathematical relationship between the two is a one-way function.
Precisely. It is incredibly easy for a computer to multiply two massive prime numbers together to create a result. But it is computationally unfeasible for even a supercomputer to take that massive result and figure out which two prime numbers were originally used to create it. That computational asymmetry is the shield.
So if a legitimate municipal operator sends a command to the reservoir floodgates,
the operator uses their private key to digitally sign the command. When the command reaches the edge device controlling the floodgates, the device uses the operator's public key to verify the signature. If the math checks out, the gate opens.
But if a hacker intercepts the transmission and tries to alter the command to open the gates fully, the cryptographic signature is broken. The hacker doesn't possess the private key to resign the altered command.
Right. The edge device receives the packet, runs the mathematical verification, sees that the signature is invalid, and instantly drops the command.
And because of the decentralized nature of the blockchain, there is no central server holding a master list of all the private keys for the hacker to steal.
It's an immune system that surrounds every single data point, every single sensor, and every single algorithmic decision with impenetrable cryptographic armor. To hack a decentralized blockchain, you would need to execute a 51% attack.
Which means a malicious actor would need to seize control of more than half of the total computational power of the entire smart city network. They would need to simultaneously hijack millions of independent nodes in order to force a consensus on a fraudulent transaction.
Which, from a sheer physics and energy perspective, is practically impossible.
It is computationally and economically prohibitive. And that is the crux of the textbook's thesis. Without the impenetrable trust and decentralized security provided by the blockchain, the brilliant intelligence of deep learning would simply be too dangerous to implement on a citywide scale. The vulnerability would outweigh the efficiency.
Exactly.
So we've mapped the entire anatomy of the future. We began with the traditional concept of a city visible, tangible, built of concrete and steel, but we've uncovered the invisible digital architecture that is already being woven into the fabric of your daily life.
It is the absolute foundation of our future urban existence.
We have explored exactly how deep learning provides the cognitive power to optimize reality. It analyzes the fluid dynamics of our roads to eliminate congestion. It monitors the precise chemistry of our soil to maximize our food supply. It uses edge-deployed decision trees to watch over our elderly and dispatch aid in milliseconds. And it mathematically deduces the quality of the air we breathe.
And we have dissected how blockchain provides the incorruptible mathematical trust to make all of that intelligence viable. It secures our most intimate medical records, guarantees the ethical provenance of our food, automates our economic interactions through smart contracts, and deploys asymmetric cryptography to shield our physical infrastructure from catastrophic attack.
All of it communicating across the lightning-fast, dynamically negotiating, decentralized terahertz waves of emerging 6G networks. This deep dive was designed to give you a structural understanding of the invisible world that dictates your environment. You aren't just living in a city of buildings, you are participating in a massive, living organism composed of algorithms, hashes, and data streams.
However, this raises an incredibly important question, and it's a concept I want to leave you to mull over as we conclude.
Oh,
Yeah. We have built this entire vision of a secure, thriving smart city on the bedrock of asymmetric cryptography, the mathematical impossibility of factoring massive prime numbers.
the impenetrable locks on our digital vaults.
Yes. But looming just over the technological horizon is the realization of quantum computing.
Machines that operate on quantum mechanics, using qubits instead of binary bits.
Exactly. And a functional quantum computer can utilize something called Shor's algorithm. Shor's algorithm is mathematically capable of solving prime factorization at speeds that make today's supercomputers look like abacuses.
Wait, which means...
Which means a powerful enough quantum computer will theoretically be capable of cracking the asymmetric encryption, the very mathematical shield protecting the entire smart city in a matter of hours or even seconds.
that unravels the entire trust layer.
It does. So the paramount question facing researchers and urban planners now is this. As we pour trillions of dollars into building these massive, data-dependent, blockchain-secured smart cities, how fast must our digital infrastructure evolve to implement quantum-resistant cryptography before the quantum age arrives and breaks all the locks?
That is a staggering reality to confront. The invisible infrastructure is going to have to evolve continually just to survive. Thank you for joining us on this exploration of the invisible city. Next time you stand at an intersection or look out over your skyline, remember, the true structure holding the weight of the city is entirely invisible. We'll see you next time.